Well, yeah. So the next talk is also very interesting. It's actually about mitigation actions for land subsidence, and this is the area of the Flevoland excursion. So for those of you who went to the Flevoland excursion, this is that area, right? So well, of course, yours.
Well, thank you very much. My name is Frauke Hoogland. I'm a hydrologist at the hydrological consultancy and research company, which is called Acacia Water. And my talk will be about investigating the effectiveness of a measure against soil subsidence that's caused by oxidation of shallow peat layers in the province of Flevoland. And this was done financed by the province of Flevoland and by the water board of the area, which is called Zuiderzeeland. So what's the issue of soil subsidence in Flevoland? Well, the province is quite new. It's only developed in the midway of the 20th century. And then it was reclaimed from the sea. And from that moment, subsidence happens, and now the surface level is about 3 to 4 meters below sea level. And subsidence continues, as you can see in the above figure, which shows the predicted subsidence in between 2011 and 2050. And here you can see that the darker colored areas would still subside about up to half a meter. Well, this subsidence has different causes. One is the continued soil ripening and compaction of the soil. And another reason is the oxidation of shallow peat layers. And these peat layers are present as indicated in the below figures, where you can see a different depth where the peat is present. And you can see the peat in brown indicated. So the problem here is that the province has an agricultural land use, which is different from most peat areas in the Netherlands, because here crops are grown like potatoes, onion, sugar beet. And these crops need also a sufficiently low groundwater level. And the subsidence is causing problems with too high groundwater levels, which requires further lowering of the water levels, and that again enhances subsidence. So there's a solution needed, and the solution that we investigated in this project was to infiltrate water via the drain system. And here you can see a schematic of the system that we applied. And usually on these fields you already have tile drainage, because the excess water needs to be drained from the fields. We adjusted that system by adding extra drains in between those existing drains, because the distance was too big. And then we connected those drains to a collector drain, which ended in a collector well. And in the well, you can control the water level. So you can also control it in a way that in the summer, infiltration is happening into the peat layer. Well, this project was about investigating the effectiveness of this measure in the situation of Flevoland, but also to look at in which areas this would be a suitable measure to apply. And that means that the project was in 2 phases. In the first phase, we looked at field sites, what the effect was of the measure. And those 2 field sites were installed here in the north in Nagelen. Wait, I can use this. Close to Nagelen in the Noordoostpolder. And the other one close to Zeewolde in the south. And there we did a lot of measurements to determine the effectiveness of the measure. And in the second phase, we determined from the insights of those field sites where the measure would be the most suitable to apply. So I will start with explaining the field sites and the measurements that we did there and the main insights from those measurements, and then tell you more about the way that we mapped the suitable locations. The 2 field sites were Zeewolde and Nagelen, and they had similar soil layering. So you have a marine sediments layer on top, which was a clay layer, followed by a peat layer, underlain by sand. And the sand extends over large areas, so the water levels in the sand are controlled by the larger hydrological system. There were also important differences, because in Zeewolde the peat layer was quite thin, At the location where we were monitoring, extended to about 1.3 meters depth. But it was not everywhere as thick. It also was very irregular in thickness. So there was a lot of heterogeneity. And at the location at Nagelen, we had a thicker peat layer, which was extending to about 3.5 meters depth. And it was also more homogeneous over the field. And at these two locations, we did extensive monitoring on groundwater levels in between drains, at different distances between the drains, and on soil moisture in the clay layer and the underlying peat layer. And we also measured the ingoing and outgoing fluxes in the drains and looked into pore water chemistry at different depths every 2 weeks. And we did some indicative measurements on bacterial communities in the peat. And for this talk, I will mainly focus on the hydrological measurements. So if we look at the first field site location, which was Flevoland, this is the site where the peat layer was the thinnest. And here we saw that the measure had no effect on the groundwater levels in the peat. So here the measure was not effective. And the reason for this was actually the thin peat layer, because this was not providing enough vertical flow resistance to independently raise groundwater levels in the peat layer without also infiltrating water to the sand layer. So actually all the water that is infiltrated directly gets into the underlying sand layer, and we cannot raise groundwater levels independently. But if we consider the presence of oxygen, then of course the water saturation in the peat is more important than the groundwater level, because the water saturation determines how much spaces are available for air entry and therefore for oxygen intrusion. And if we look at the water saturation in this location, I'm sorry, I forgot to tell you something. First, water saturation down here. You can see the water saturation at the reference plot and at the mitigation plot, because we always had a reference plot next to the mitigation plot to see the differences. They both stay quite close to 100% water saturation, also in the summers of 2018 and 2019. And I also indicated here a value of 85% water saturation, because this is sometimes used as a rule of thumb at which water saturation you would get oxygen intrusion. For example, in fields of archaeology, you can find this where they estimate whether wooden objects in the soil are at danger of degrading. Or for example, in the field of agriculture, this can be used to indicate whether crops are having oxygen stress. So we use this value to estimate whether oxygen is present in the peat layer. And these measurements were done on the top of the peat layer, or in the top of the peat layer at 70 centimeters depth. And they indicate that actually the peat layer remains quite free of oxygen. So there's a low risk of oxygen intrusion into the peat layer. And the explanation for that is that peat has such a texture that it can hold on to water quite well above the groundwater level. And also because there is a presence of a clay layer, and the roots of the crops are mainly extracting their water from the top clay layer. So they're not affecting the drying of the peat layer. And in the top figure, I have an illustration of the connection between the sand and the peat. So here you can see the water levels as measured in the peat layer, which is the lighter blue continuous line, and in the deeper sand layer, which is darker blue. And you can see that except for in the summer when the water level drops below the sensor level of the peat layer, that the other times they were very similar and they were following the same dynamics. So there's a direct interaction between the peat and the sand, and yeah, they are like acting like one hydrologic system. So the results for the other field site at Nagelen were quite different, because here was possible to raise the groundwater levels in summer. And you can see that in the top figure, where you can see the water table depths in the peat, in the mitigation plot in red, and the reference plot in blue. And this during the summer in 2019, and the maximum difference was 30 centimeters. And this was measured in between drains, so it was effective to raise groundwater levels. We did, however, also see that the vertical flow direction changed because of the measure. Because at the reference plots, at both locations, we measured the water level in the underlying sand. And at the reference plots, the direction was upward seepage flux, because the pressure was higher in the underlying sand. But at the mitigation plots, because we raised the groundwater levels, the direction changed to downwards flow. And based on the fluxes that we measured, we could also deduce that about 30 to 40% of the infiltrated water actually gets lost to the underlying sand layer. So this means that also the thickness of the peat affects the ability to raise groundwater levels, but also the amount of water that you need to raise those groundwater levels. Well, here for the water saturation, we see a little bit the same image as for Zeewolde, where both in the reference plot and the mitigation plots, the water saturation remains quite high, also in the summer, close to 100%. And this can again be explained by the texture of the peat, which has a good water retention. So also with large capillary forces, it can retain water well. And the presence of the clay layer, which was mostly providing the water for the crops. Well, in the second phase, we used these insights to map the locations where the measure would be effective. And we did this in several steps. First, we had to define some general criteria to determine which location the measure would be effective. And we did this based on those field sites insights and based on model scenarios, which we performed with Hydros 2D on the parcel level. And then we applied those criteria spatially using quite detailed soil maps of the region, which are available, which you can see here below. And they indicate the thickness of the mineral top layer, the thickness of the peat layer, and the starting depth of the sand layer. So we could use all those information to map the right locations. We also used the map of the lowest groundwater levels in summer, which was the result of a regional hydrological model. And in addition, we also consulted some agricultural experts in the region to see what additional risk factors have to be taken into account if a farmer would decide for this measure on his field. So first I will tell you how we defined the criteria. Well, the first criteria that we had to define was when there is a risk of oxidation of the peat layer. And this is schematically illustrated with this figure. We said that when the peat layer extends in the root zone of the crops, then it's a danger of being of oxygen intrusion. Because usually the crops extract water and the roots wouldn't grow into anaerobic parts. So that's, in that case, the soil is in danger. In addition, the peat layers that are below the rooting zone are in danger if the groundwater level drops far enough. And this is based on the soil water retention curve, so of the water holding capacity of the peat. And we determined that with typical water retention curves of the peat that we find in Flevoland, this distance will be about 60 centimeters above the groundwater level. So when the peat is present 60 meters or more above the deepest groundwater level, then there's also a risk of oxidation. Well, the second criterion that we had to define was when the measure would be effective to raise groundwater levels. And this we based on the insights from the field and on the modeling that we did, where we varied also the thickness of the peat layer. And this is mostly dependent on the ending depth of the peat layer. Well, of course, when it's not like a discrete value that at this point it works and at this point it doesn't work. So we had to find it somewhere in between. But when the peat layer increases, then the effectiveness also increases because it's easier to raise the groundwater level and you lose less water to the underlying sand. So we chose the boundaries that when it's extending less than 1.5 meters below the surface level, then the measure is not suitable. So that's the case for the field sites in Zeewolde, for example. When it's in between 1.5 and 2 meters, then it would be moderately suitable, but you would have to check also in the field. Yeah. And when it's deeper than 2 meters, then it should be suitable. So these criteria we could use to apply on these soil maps and the deepest groundwater levels in summer, and to indicate the locations where the measure would be effective. So in this map, all the colored areas are the areas where actually the peat is at risk of oxidation by oxygen. And the colors indicate whether the measure would be effective there. And you can see that there are large areas where it wouldn't be effective because the sand layer is at too shallow depth. So you cannot use this measure to protect the peat layer. And well, this map is an indication for the province of where they could find the areas where they could apply this measure. But because the coarseness of the maps underlying it, if you want to decide at parcel scale what you want to do, then you still have to make a field assessment, of course, and check whether these conditions are present really in the field. Also, in consultation with the agricultural experts, we saw that there is, of course, a challenge to combine land use with raised groundwater levels, and that the farmers have to have the knowledge when to manage the groundwater levels such that the crops don't experience oxygen stress and you don't have texture losses. So it brings me to the summary. We saw that the effect of the measure depends largely on the soil buildup and hydrology, and the extent of the peat layer defines or influences whether it's possible to raise groundwater levels and how much water will be lost. A risk of oxygen intrusion is most directly related to water saturation, and the water saturation can remain high when there is a top clay layer in which the roots mostly extract their water from, and when the water retention of the peat is sufficient. And based on criteria, we could map the suitable locations. Well, thank you very much for your attention.
Yeah, thanks for this nice presentation. Are there questions?
Yes, thank you very much for the nice talk. Very interesting. Did you consider the different soil properties of the peat layer with depths? Because in my experience, it's more dependent on what kind of soil properties you have than how the extent of the peat layer is. Because usually you have those own water levels in peat layers when you have some kind of layer with low hydraulic conductivity in the bottom. Mm-hmm. And then it doesn't matter if the peat layer is 2 meter or 3 meter above.
Well, we chose the properties based on the field insights. So the modeling was done based on the hydraulic conductivity that we found in the field, and then the horizontal conductivity was different from the vertical conductivity. But we did not find indications that there should be a layer that's really low in conductivity below, because we still saw from the flux measurements that also a lot of water is lost to the deeper sand layer.
Okay, thank you.
Yeah, a lot of questions. Jan.
Thank you. How did you measure the saturation degree? I mean, did you take samples or?
No, we had continuous soil moisture measurements in the clay layer and in the peat layer at different depths.
Okay.
Yeah. And then we translated that to water saturation by using the maximum value, which is the porosity value.
Yeah. And how did you have the maximum?
So we found the maximum in the time series of the sensor, which should be the porosity value. So the value that you find in winter, for example, when it's saturated.
Thank you.
So 2 short questions and then yeah.
One very nice. One question is, did you play a bit with the distance between the drain? Because I can imagine that if you put the drain much more close one to each other, this can work more better when the peat is thinner. Yeah.
Well, yeah, that can be a solution for the areas where we said based on the field size and the modeling, it's only moderately suitable. Then, of course, a solution could be to put the drains closer together. But at the field site it was 6 meters, and at some point, if it's really thin, then like I'd say Wolde, even 2 meter distance would not suffice. You would still have direct flow to the underlying sand. So this could be a solution in the areas where we say, okay, it's moderately suitable, but a lot of water get lost. But yeah, but still it would mean a lot of water loss as well.
Hank, is your question short?
Oh, so question. The water loss to the underlying sand layer is an issue important for the effectiveness, but you studied this on a small plot where you use this. If you would do this system over many square kilometers, the water loss to the sand would be actually contributing to the adjacent field, so the effectiveness might be enhanced. Did you consider that?
Yes, that could be, but we looked into this measure as a measure that the individual farmer could decide on. So we didn't look at, it's right that if we put it in large areas, then the effect would probably be different. But still the sand is quite widely spread and well conductive. So yeah, but we would have to model then those cumulative effects. Yeah.
Okay, thanks.
Okay.